happening over. What do I mean? Let me just take a little side step first. Imagine you go to a bus stop, okay? Yeah. And you see somebody waiting at the bus stop, all right? And you are very, outgoing, so you don't mind talking to them and asking them questions. Yeah. Just imagine this, okay? And you go up to them and you say, have you been waiting a long time for this bus? Yeah, why not? And they then say, gosh, yes, I have. If you then found out that they've been waiting almost 12 seconds for the bus, you'd think they were mad to say they've been waiting a long time if they've been waiting 12 seconds. Yes? True? If you then, if for example, you found out they'd been waiting 17 years there, that would also seem mad, wouldn't it?
Yeah.
Yes? Why does it seem mad? Well, it seems mad because you have an instinctive, not instinctive, you've experienced the world. You know how long people wait for buses. Well, it's 10 minutes, isn't it? That's 5 to 10 minutes is your ballpark figure, isn't it? And so when somebody says to you a long time, I've been waiting a long time, or maybe they've said, I wait a short time, what they mean is in comparison to 5 or 10 minutes, I've been here a minute, that's a short time. I've been here half an hour, that's starting to get a long time, isn't it? You get it? So there's a time scale which characterises, how long you wait for buses. Right? Yeah. This is sort of similar to that. It characterises how long things take to reorientate in your sample. It doesn't mean they all reorientate on that time scale, but that's the kind of typical time scale that they reorientate. Like the buses, you typically wait 5 or 10 minutes.
What's reorientating?
Okay, next thing. But you get the idea that it gives you a feel for the time scale of whatever this thing I'm about to talk about is about. Okay. Reorientation, well, if you think about dynamics, here is my pen. Okay. Mm-hmm. Imagine it's a molecule, and it's inside some liquid, and you're watching it. There are 2 types of motion. There's many, but there's 2 that we can think of in particular. There's translational motion. Translational motion is when I change my coordinates. So that's maybe my x one, maybe that's my y coordinate, and that's my z coordinate. Diffusion is typically about translational motion, though people do talk about rotational diffusion. I have to say that quickly there. Okay, so this is all translational motion. On top of that, as well as that, is rotational motion. There we go. So I'm not changing my coordinates, my x or my y or my z, but all this kind of stuff is rotation. Usually they're together, aren't they? That's happening in life. Yep. Okay. So this thing is quantifying not the translational timescales, how long does it take to kind of move its own distance, maybe that's what you think about, I don't know. Okay, we're thinking about how long it takes to rotate. Yeah? Okay. So this is a rotational correlation time. So as things get hotter, typically things move quicker. If they move quicker, they take less time to reorientate. So the correlation time will reduce with increasing temperature, which is what this describes. It also has, though, in it, a glass transition, or ideal glass. Remember we made that difference last time? Ideal glass transition temperature. So when we get to T0, this thing is slowing and slowing as we come down in temperature, and it's getting slower and a little slower. And this correlation time is getting longer and longer and longer, larger and larger and larger. When we hit T0, that happens. And the time scale for it to reorientate is now an eternity. You have to wait eternities for this thing to reorientate. It's a glass, it really is. Got it? That's what this is.
Like you could say it's just orientated.
It's the reorientation, not yes, it is oriented. I'm talking about the reorientation, so that's it changing its orientation.
But if it was always at T0, how do you know what its initial orientation was? So
there is no such thing as initial orientation. What are you talking about?
So like you're saying, you need to
when you look at it, it looks like that.
Yeah.
That's the only thing that means by initial. When you choose to look at the system, it happens to be like that.
Yeah.
Yeah. How long before it moves from that to something new? That's
what you're working.
That's what that tour tells me. If we're at T0 or below, you look at it. Oh, there we go. And it will take an eternity from that point. It just happens to be like that.
Oh,
this molecule over here happens to be like that, and this one over here happens to be like that. There's no, there's no special magical initial conditions.
Right.
All I mean is that you started your stopwatch there because you looked at the system. You went tick and looked. Yeah, and then how long is it going to take to move? It takes forever.
Right.
Got it? Okay. So we now know, and this thing here is just a prefactor. This is just some number that gets these numbers right. Yeah. This is the temperature dependence. And this is just some time scale that gets this right. That's all that is. There's some interesting physics actually hidden in this parameter, but we've only got a few weeks, so what the heck. Now we get to your point. Pseudo activation energy. Well, first of all, it's just a number, isn't it? It's just something that makes this fit the data. So if you actually measured this, this is something that just gets it right. You know, do you need a number 1 there, or 42, or 0.7, or 10 to the minus 27? You need some number there, so this gets the right temperature dependence. So in reality, it is what's called a phenomenological constant. It's just a number that we use to fit the data. But your question is, let me turn the question around a little bit. Why is it called pseudo activation energy? Why call it such a fancy name? Okay. The reason is because many dynamics reorientations, okay, follow this behavior. Okay, so this torr is you're measuring some other molecule now, and this is its correlation time.
Yeah.
And many molecules, like water molecules, for example, follow this law, not really this one.
Yeah.
Well, actually, this one and this one are the same. You just let T0 go to 0. If you put T0 to 0, these two are basically the same. Okay, right. But many molecules just follow this simpler version like this. So that's your correlation time. That's some prefactor. There's your E. You've got a 1 over T dependence, look. Your T0's eventually gone to 0. This R is the molar constant, 8.31 joules per Kelvin. Yeah, and that is now an activation energy. That's what that's called. Now this, you probably haven't heard of this before. This is called an Arrhenius dependence. Arrhenius, there's a famous scientist, 19th century perhaps. Arrhenius, Arrhenius. Arrhenius. You've heard of him? No? Well, what he did, he studied chemical processes. So you're mixing two chemicals together to get a reaction. How quickly does that reaction proceed at? Or what timescale does the reaction take place on? And he came up with this, that the timescale for the reaction depended on an activation energy and a temperature. See? So if you made the thing hotter, the time it took for the process to happen became shorter, 12 became smaller. And he found that many processes, all sorts of different things, followed this kind of rule, not just chemical processes, but physical processes too. This happens, you bored yet? I could do a whole lecture on you know. This happens, why does this happen? This happens because of this is the kind of, you can actually model this, okay? So any process that kind of follows this, what you say is there's some energy landscape, all right? So this is energy as a function of, maybe it's position. Maybe I'm moving a molecule from here to here, and then there's an energy landscape, so it's very difficult to be here, very high energy, big cost, or it likes to be here, low energy cost, talking loosely. Maybe it's about reorientating, and then this is high energy cost, this is low energy, this is high energy. Yeah? It could be some chemical pathway. As the chemistry is happening, we're moving along this axis. It can be a very general thing, all sorts of different things. Let's think of it just as position X. Yeah? What you have is you have an energy barrier like this. So you start over here, okay? And you're at this, you've got this much energy. That's how much energy you have in life, yeah? And you're over here, and then you're sitting here. But look over here. There's a lower energy over here. So maybe this corresponds to this configuration, and then over here, that corresponds to that configuration.
Mm-hmm.
This is the lower energy level, but you're sitting over here, yeah? So how long would it take for you to get into this configuration? How long would it take? You know, you're trapped. You're here. And how long does it take for you to go into this one? That's the question. Well, it can be mathematically modelled. What happens is you actually vibrate against it. You keep hitting against this wall. Can I get through it? No, I can't. Can I get through this wall? No, I can't. Can I get through this wall? No, I can't.
Until you get the activation energy to go past.
Yeah, and because there's a Boltzmann distribution of energies in a thermal bath, so sometimes you've got a lot of energy, sometimes you have a little less. Yeah, all the molecules in this room are moving, some are moving faster, some are slower. So just by chance, as you go backwards and forwards, I'm going to get through this wall, I'm going to get through this wall. Yeah? Sometimes when you hit there, you've got just the right amount of energy, that's the Boltzmann factor, just by chance, that, over you go. I made it. And then you're in here, and you go, I like being over here. I mean, you can pop back again as well. Mm-hmm. But that's what happens. That's the barrier, and that's why this is called an activation energy, because you have to have that much energy to activate this process.
Yeah.
This is called a pseudo activation energy because it looks a bit like this. That's all, but it's not really an energy, so it's it's not really the same. There's not the same logic behind it.
Yeah.
So people call it a pseudo activation energy. There you go, so you now understand this a bit better, maybe, hopefully. You know what this term is, you know what correlation time is, and you've learned about Arrhenius dependence. Ooh, this comes all over the place, this thing. So whenever people plot log of some process, like a time scale or amount of substance, against 1 over temperature in Kelvin, what they're doing is they're looking for an Arrhenius. If you plot log of this against 1 over temperature, you get a straight line. So they're looking for a straight line dependence. Go, yes, it's Arrhenius. And then they can actually determine the activation energy and go, that's the activation energy for this process.
Does that break down at very low temperatures then?
Well, it's actually quite the opposite. Is it tends to become true at very low temperatures.
Really?
Even this one. So if you go below T0, you actually find a new process will come in where it follows this. So, so actually it tends to, this is, yeah. So it depends what you mean. I mean, over a small temperature range, this will appear to be true.
Okay.
You know, but so even if you have something that really does this, okay.